Good morning to one and all. Here we are going to learn about cathode ray oscilloscope. So, what is cathode ray oscilloscope? It is a multi-purpose display instrument used for observation, measurement, and analysis of waveforms. Uh, First, what do you mean by waveforms? Let us take a sine waveform. So when it comes to waveform, as you can see the form of the equation or the line is in the form of a wave, which is ups and downs. So how a sine curve will be. If drawing like this, just as an example, I'm drawing. So look at it. So it will be somewhat like this. So this will be the maximum point and this will be the minimum point, and this will be the point at which the value is 0. This is a sine curve. So this is a kind of waveform which is sine waveform. Cosine waveform is 90-degree behind it. So these are the waveforms. So why we need this waveforms to be checking is that for the AC supply is given to the devices. So we need to check how the waveform and how the output is going to be. So if for suppose amplitude of phi is given inside it and we are amplifying it and taking it as 10, so we need to look into it whether it is amplified or not. So in that scenario, we are going to use this, which is an amplifier. So using an amplifier, we are able to amplify the signal. But how do we exactly know it is amplified or not? But by using a wave. See this wave. Let this be the wave. It is sloppy, but uh, just get the gist of it. Now let the maximum amplitude for this be 5 and this be 10. So you can see that the amplified signal is this. So blue line is clearly amplified, but from the 5 voltage line. So using this comparative waveform, we can see that the device has successfully amplified the signal. So for this kind of purposes, we are using this cathode ray oscilloscope. Now this is the introduction of it. Now CRO is generally XY axis plotter, which means inside the how it will be is like this. So this will be output of a cathode ray oscilloscope. There will be, as usual, there will be several divisions here. So according to the knob which it is given inside outside of the box, we can adjust the time frame of it. This is time axis T, and this will be the axis of amplitude, which will be generally voltage. So in terms of voltage, we know that voltage will be V cos omega t or V sin omega t based on the devices which we are using. So this is what a CRO is, which is XY plotter, which means it has only two axes. So here on a single screen, it can display different signals applied to different channels. As I said, comparatively, we can know that. So for example, mm, say that we are using an amplifier here. So let this be an amplifier. There will be a lot of signals. So I'm just trying. Let this be an amplifier with this as VRF pin, and this will be the ground pin, and this will be the input, and this will be the output. So according to the ref, it is amplitude. So we'll take output from here, which will be let the wave be 1. So let the wave be 1. Now we are taking output from here. Let this wave we give connection to the second port. This will be for first port and this will be for second port. So what is this device? This is an amplifier. So we should be able to differentiate clearly that the signal from 1 is greater than 2. So it can be amplified negatively or greatly. So amplification means adjustment or amplifying the given signal, increasing or decreasing. The amplification doesn't only mean that we have to increase, because we can also decrease the value. So based on this, we are able to, based on the using CRO, we are able to distinguish between two curves, which means having multiple channels is far beneficial than having a single channel. So it can measure amplitude, frequencies, and phase shift of various signals. Which phase shift just says that if an angle is starting, if the input angle is starting from zero, but the output is starting from some other term, which is like pi by 2, pi by 4, or something. That is the phase shift. That is the phase angle between the input and the output. And frequencies will be dependent on the inputs which we give. Many physical quantities like temperature and x y is not fixed. So y will mostly x will be fixed as time axis, and the amplitude, the y axis will be varying according to the devices which we use. Now here strain can convert into electricity by the use of transducers. So transducers generally, let us take simple example, which is piezoelectric crystal. So here, when we use a piezoelectric crystal, the mechanism of piezoelectric crystal is when we give mechanical input, will give will get the equivalent electrical output, uh, vice versa of it. So that is what electrical signals can have transducers and signal can be displayed. So these electrical signals you give it to the connection to CRO probes. From that we'll be able to get the output. Now, a moving luminous spot over the screen displays the signal. So, as I said, the output will be somewhat. This will be the display screen. This will be the expected order. So it will be divided like this, and there will be multiple grids here. So like this, there will be multiple grids. So here the light won't be of any multiple colors which we use, which is this is not a digital oscilloscope. So we'll get to that later. A digital oscilloscope is generally a cathode ray oscilloscope, but it has more than one channels, and the values of the frequencies, amplitudes are just given by it. We know need to have to check it for the for taking the output. So it will be predetermined when we just connect it. So here the moving luminous spot over the screen displays a signal. So there will be a thing. We'll get into that part cheaper later. Now CRS are used to study waveform. As I said, it is used to study waveforms and other time varying phenomena. That's the main word which you need to see here. See, which is time varying phenomena, which means the x-axis always fixed, which is time axis. So this x-axis is always a time axis. So y will be changed based on the type of input or device which we are choosing to do. And we can range it from very low to high frequencies, as we know that frequency is inversely proportional to time, and we can thus find it. Central unit of the oscilloscope is the cathode ray tube, from which we'll get a stream of beams. Based on the beams and horizontal and uh, vertical amplifiers, we are able to get a broadened signal of it, which will fall on the special phosphor screen, which will illuminate as a neon green or whatever, a neon greenish color like that. uh, Based on excitation level from the heat and the excitation level from the cathode ray tube, we are going to see the output, and the remaining part of the CRO consists of the circuitry required to operate the cathode ray tube. Now, this is blocked on the cathode ray tube. Before getting into it, let us see the components of the cathode ray oscilloscope. So the main component is, as I said, CRT, which is cathode ray tube, and a vertical amplifier, delay line, horizontal amplifier, time-based generator, training circuit, power supply. So each of these components have a specific function, so that they are combinedly called as a cathode ray oscilloscope. Okay. For the power supply, CRT needs a huge amount of power supply. Various other all components need a minimal amount of supply, which is like 5 volt, based on the components or the materials which we use inside it. As it provides greater voltages required to the greater grid to generate accelerate electron beam for CRT. So it requires, as I said, CRT requires high voltage for pre-accelerating and accelerating anode, low voltage for heater, control it, focusing, and other circuits. Other circuits means distributing circuit, time-based generator, horizontal amplifier, delay line, vertical amplifier. Now let us see a diagram of it before getting into it so that it will be a bit helpful for us. Here is a diagram. So this is cathode ray oscilloscope. We have a vertical amplifier, a relay line, the trigger circuit, a time based generator, horizontal amplifier, power supply, and this is the cathode ray tube. So this is the main part where will get a state of beam. Here we'll have a screen. So determine this is a screen. So when these beams pass, first they are vertically amplified. It will be somewhat like this, and then they'll be horizontally amplified. So the signal will be like this. So this signal will fall on the screen, and we'll be able to see it as a waveform. So this is the general idea of the cathode ray oscilloscope. So these are the various components which I use. We'll get into it part by part. Now power supply here. See the power supply. The high voltage is directly given to CRT and low voltage to amplifier and sweep. As I said before, amplifier is not only to amplify the signal, which means not only to increase the signal. Amplifier doesn't mean only increasing but also decreasing the voltage which is amplitude of it. So by using the amplifier, we are converting the high voltage to low voltage supply and sweep is to maintain a constant level of it. So pass appearance. So vertical up. The signal under the analysis is to be vertically deflection plates through vertical amplifier. Now uh, let us go into the cathode ray tube first, and then we'll get into other parts later. So cathode ray tube. So see this right here. There are connecting pins. Here we give high voltage. Okay. Here a high voltage is given. This is electron gun. So the electron gun will be somewhat like this. So this will be the cathode, and here will be the heater. This is heater and this cathode ray tube. But now we are giving a high supply to this. Okay, remind of it. We are giving a high supply to this. So here this will be a coil. So this will be somewhat like this, a coil. You know what generally a coil does? The voltage flows through it and magnetic flux linkages to due to these magnetic flux linkages, the coil gets heated up. This heated up here, since we are giving high voltage, it will be more and more hotter than normal coils, and falling on this cathode tube, which is generally cathode, the electron are ejected from this cathode. Okay, you know the scattering effect, right? So as it falls, it doesn't concentrate. It doesn't get concentrated. So we have multiple concentrated pins here. One, two. Generally, there will be three concentrating pins. So here there are three pins. Okay. So what will be the usage of three pins and how they are used to concentrate the signal? First, these two will be of higher supplies. First and last will be higher voltages. So which will be more than 100, I guess. So higher voltages, and the second will be of lower voltage. So what are the names of these pins? First will be pre-acceleration pin, which means it gives energy for the electron beam to accelerate at the speed. And then B will be second will be the focus pin. It focuses all the emerging lights into a single point so that the output signal is far more clearer than it is. And then this will be the post acceleration. So first we have pre electron gun. From the electron gun, the electrons are scattered or ejected from it. From that base, from falling on this focus nodes, first it will get pre-accelerated, followed by a focus node, and then post acceleration. Now this post accelerated signal, which means it has a fast and fast, which is like free within a small small frames of seconds, this beam gets to onto this as a single point. So always keep into mind we haven't given the input signal yet. That's why how it will be a single point. So now here there is no input. So don't go into the diagram deep into it. Let me clear the screen. Now here the inputs. How are the inputs given? By this, which is vertical electrode and horizontal electrode. Now, based on this, we are able to give the signal. Exactly how? Let us get into it. Now, here the electron, let me just a bit. Now, the electron gun from here as a single point, this is going through this vertical plate. The vertical plates are in this V. So, it is given a charge, which means it pulls towards itself. So it pulls from the beam towards down, the upper beam towards up, which means let this be a cross section, which means it will be a single point here. Okay, the single point when it is passing through this vertical amplifier, what it happens is it gets a line, which means only the amplitude of the signal is seen. So initially it had no amplitude, which is zero amplitude. Passing through vertical amplifier, we are able to see the amplitude of it, which is the extent of its value. Now, this we a single line we cannot call it as a waveform because it is a wave, a kind of wave, but exactly not in waveform. So what we need to expand in a horizontal anode. So this horizontal anode is keeping like this, okay, parallel base. It also works as same as the vertical amplifier. Here a straight signal is passed, it will take towards itself and this towards itself so that the single line is splitted. It is same as how we open a Doritos packet. You know that it is a single line straight. When you open, it expands, and there will be a sun. When we open, it is like open of an eye, which is a waveform, right? Similar to that, here it doesn't exactly open, but the waveform is open. You get it right. So, and this is the function of a cathode ray tube. Exactly how it is, and a screen is made of phosphor. So H is a horizontal electrode. These are electrodes, and there will be pre-acceleration electrodes, a post-acceleration electrode, and then a focus electrode. The post-acceleration, pre-acceleration electrodes are far higher value. Okay, so get that in mind. Now, electron gun or electron emitter, the deflecting system, the fluorescent screen are the three major components of a general purpose CRT. What is electron gun and emitter? This here I said there will be a cathode followed by heater, so that altogether with this focus, pre-acceleration, post-acceleration nodes forms an electron gun or electron emitter. So electron emitter doesn't, we don't need a scatter of electrons because we can't concentrate it using a vertical amplifier. So when we give a scatter of electrons, the plates, the beams which are electrons which are near the plates get attracted, which is gets towards it, not falling on the screen. That's why we focus the electrode as fast as possible so that it doesn't get attracted towards these plates. That's why we have post acceleration, focus, and pre-acceleration. Now, what is the deflection system? The deflection system are these two, which is vertical electrode and the horizontal electrode. Uh, and deflection system. So, from the electron gun, which is electron emitter, we get a single dot, and those are getting transformed into a waveform, which means it deflects that single point of electrons into a waveform. So, single point is taken into a waveform. Okay, remember that. And then how we are going to display it? We just have an electron beam, which is electron beam, which is just electrons. So how we have a special screen known as phosphor screen. So what will we be doing on this phosphor screen? So it is illuminated with a phosphor when these electron beams fall on it. So let me check if I have the right color. So there is no right. It will be somewhat similar to dark green, and this waveform will be of this color. So when the electron beam falls on this screen with phosphor, the dark green phosphor gets excited. When it gets excited, it excites a color which is light green in color. So based on this excitation, we are seeing a waveform. So this is cathode ray tube. So see, we have elaborated notes on electron gun deflection system. Let us go through it quickly. Now in the wait, let me just now here we see about the electron gun. As I said, the explanation is given. This is just the overview of it. So in the electron gun of CRT, electrons are emitted and converted into sharp beam based on and focused upon the fluorescent screen using the focus electrodes. The electron beam consists of an indirectly heated cathode. As I said, the cathode is in somewhat the shape. Emitting electrons is an accelerating electrode and a focusing anode. As is the control grid, it comes later after that. So control grid is what like this, like funnel type. So the first and last, the pre-accelerating and accelerating arrow focus on the control grid. A control grid is mostly this totally kind of this. So using this control grid, which is the supply of these, we are able to focus the scattered electron beams of the cathode. Now these electrodes are connected to the base pin, which is this, and based on that, the cathode emitting the electrons surrounded by control grid with a fine hole at its center. So this is what the fine hole is. The accelerated beam passes through the fine hole. The negative voltage at the control grid controls the flow of electrons in the electron beam, and consequently the brightness of the spot on the CRO is controlled. What happens here is that it consists of negative voltage. So we all know that negative repel each other, positive repel each other, and opposite signs always attract each other. So opposite signs always attract each other. So we need it to be concentrated, not scattered. So we use the same signal as the flowed electrons from it. So electron negatively charged. So we use a negative electrodes, which are accelerating electrode, focusing anode. So here we use anode. Check into that. And then the negative voltage, the control grid controls the flow of electrons in the electron beam, and consequently the brightness spot on the CRO skin is controlled, which is what is find out without any input. Is it? On deflection system, hydrostatic deflection of electron beam is used in general purpose oscilloscope. Here, the deflecting system consists of a pair of horizontal and vertical deflecting plates. So, see this, they have a pair, which is two on both the sides. So, we'll get the reference point as the middle of the axis, which is where the point beam is faced, and equally spaced from the midpoint of it. So take this as an axis. For instance, the emitting focus accelerated beam of electrons as the axis, and we'll keep these two plates at equal distances from it, and horizontal plates horizontally equal distance. The deflecting system consists of a pair of horizontal and vertical plates. That is considered two vertical. Let us consider two parallel vertical plates. Let this be P1, P2. The beam is focused at the point O in the screen in the absence of which is the center point, which is O. So this is center point O. If a positive was applied to plate P1 with respect to P2, the negatively charged atoms are attracted towards the positive plate P1, and these electrons which focus the point at Y1 on the fluorescent screen. So uh, let me highlight the plates here, okay? So since it is vertical plates, this the plate 1 and plate 2. These are parallelly spaced, and the beam is at the center. Now it is negatively spaced. Okay, you know that the beam is negative because electrode. So this is positive. So these two plates are positive. Now what I said, they attract towards each other. So this electron V is pulled at this point y1, and so this we plate P1, okay, P1, and this plate P2. So this also is positively charged. Due to the pull, we have here X, okay. So this position B by 2. So adding these, which is y1 plus y2, is the total amplitude of the signal. So y1 plus y2 is the total amplitude of the signal. Okay, now we know that the signal is amplified vertically, so it is not exactly a waveform of a signal. It can be a DC signal, but horizontal alone does not defy the vertical only depicts the amplitude of it, but not the time frame or the frequency of every signal has a certain frequency. So we need to check into that. Okay, so for that we have horizontal planes. So this is the axis, and this is the B. Okay, this is the vertical B. Now we have horizontal plates here, here, the same here also. So this will be positively charged. This is also positively charged. Both plates positively charged. Now what happens? This signal gets pulled towards here, and this signal pulls towards here. It can happen in any other way. Subsequently, we'll get for a sine signal, if we get a direct input for checking, so we'll be getting somewhat like this sine signal. So this will be the deflection systems concepts. And then what we'll be doing, this is horizontal. Now the reflection proportional to the deflection voltage within the plates. The polarity of the reflex is reversed. The plot applies it by 2 show. Now see this. This is positively charged, and this is negatively charged. It This is getting attracted towards the positively charged and repel, so this goes to the point y1. So this will be the axis of it. Okay, this will be the amplitude of this total. The amplitude of it. Now next, deflection system. This is horizontal deflection system. So only single line does not depict the state of a signal or the waveform of a signal. For that case, you'll be using horizontal deflection system. To deflect the horizontal beam horizontally, an alternating point is applied to the horizontal deflection spade and spot on horizontal. Here it is parallelly, both are parallelly spaced, both vertical and horizontal, but the position depends on how it is placed. So horizontal is placed on the above, and exactly adjacent to it, it is placed here. As you see, the horizontal plates are horizontally to the electron beam. So here, this is positively charged and this is negatively charged, and vice versa. So when this negatively charged beam is passed through the plates, this gets attracted towards here. So this will be the main beam, which is from the focus beam from the electron gun, and this is the deflected beam from the passing through the electron plates. So it is going to the x2, and x1 x2 will be the time frame of it, which is total time taken. Now this is the deflection system and display of waveform. Let us see this. So as I said, A, B, C, this will be the waveform of it. Okay. Now this will be the round screen, and this will be the axis, and this will be the midpoint of the axis. So first, when it passes through the vertical amplifier, it is seen as only this signal. So the single line, this will be the waveform after the vertical amplifier. After the then passing through the horizontal, this will be the signal. So we can see what is happening after the vertical amplifier and the horizontal amplifier for a single focus beam. So input to the horizontal plates. So as we can see the plates, when we just uh, draw a horizontal diagram for this, this will be like a ramp signal. Ramp signal is nothing but a signal which is continuous, increasing continuous with time. Now the screen, let us go to the diagram, and then yeah, after the vertical amplifier, horizontal amplifier, now we seen the cathode ray tube. Okay, cathode ray tube is done. Now vertical amplifier. So the signal under the analysis is applied to the vertical deflection plate to the vertical amplifier. Now this is the input signal. Okay, and we give a positive signal. We give a signal, not positive. My bad. We give a signal levels. Okay. First, it is vertically amplified. Amplified means it can reduce or increase. So for suppose we are giving a zero point 0.5 volt of input, we need to get a 5 volt input. So we multiply it 10 times. The, uh, the knob is turned so that we get the amplified signal. So here we get the amplified signal which is 5. Okay. To the delay line. We'll get back to my delay line. Okay. Let us see how it is given here. So immediately delay line. My bad. Now the general talk here. We know that electron beam passes so fast. Okay, so fast. It's, like fraction of seconds will be on. As soon as the coil gets heat, the cathode rays are given out. As the input is already given, the focus electrons get the voltage, and then it is focused in a single stream of beam after passing through vertical and horizontal amplifier, and output is given on as fluorescent screen. Now, how should be the voltages of vertical and horizontal amplifier? Okay, first we are given vertical amplifier A. Sorry for the delay. Sorry, because the inconvenience has some background issues. So, delay, why delay? Okay, I was stuck there. So, the signal, the input to the vertical and horizontal amplifier should be at the same time. So, get to the point, should be at the same time, which means the signals are too fast, but still there is frequency like a 3 to 13 nanosecond gap when it is directly given than the horizontal amplifier signal. See, let us see the diagram first. Here, the vertical amplifier, let us forget the delay line. Okay, vertical amplifier is directly given here. After the vertical amplifier, the input is given here. Here, the amplified signal, horizontal signal is given into the output. Now, this same signal through here is going to and trigger circuit, which triggers the circuit, and then a time-based generator which changes the x-axis into y-axis based on the input and the type of output which we require to that horizontal amplifier, so that the signals is horizontally amplified. So here the signal isn't horizontally amplified, but the power that needs to horizontally amplify the beam is given to the horizontal amplifier plates. So this is going through a time taking concept of process, okay, right? So rather than going, so from here you are going to a place, and here you are taking a D route, like come here, go back, taking D route here, then finally come. Which is quicker? The straight line is quicker. You get the point, right? And here we have many obstacles also in this route. So we can clearly see that the vertical line is reaching the uh, cathode tube way faster than the horizontal plates. That's why a delay line is used. So what is a delay? Uh, in English words, a delay is to postpone something or uh, continue after a brief amount of time, right? After a brief amount of time. That's why a delay line. Vertical amplifier signal is given to the delay line, which delays the input, so that we pre-calculate how much the delay line signal should be, how much the input should be delayed. Because so we first run it, and then we check the timing for the horizontal amplifier place to get charged. So that based on that time, the delay lines are chooses dependent on that. Okay, let us see. A delay line, if both vertical and horizontal signals arrive at the same time, the corresponding deflection rate, then only we will get the exact waveform. As I said, both the signals should be at the same time, so that the passing signal is both horizontally and vertically amplified. So, but the vertical signal arrives much early compared to the horizontal signal, as it has no obstacles when you see. That's right. For this reason, the vertical signal at the output of the vertical amplifier should be delayed with the help of delay line. The delay time is almost equal to 200 nanoseconds. See the time for it. It is still nanosecond. We need efficiency, the exact input output exact waveform what. So for that calculations and for that convenience for the customer, there the daily time is 200 nanoseconds, which is like very. See, we know that nano means 10 power minus 9, macros minus 6, millis minus 3, 10 power minus 9, which is way less than a second. It's just uh, a, even a time, a brief, small pause. When I'm speaking, a small pause is 200 nanoseconds. So even if it is just that small, you can ask me that why such small efficiency need, why that small time delay line is needed. Because when the amplified signal is outputted, it gets charged horizontally. So we'll get a mixed wave of signal. First, it gets placed on the phosphor screen, and it will remain charged for some seconds for this small frame of seconds, 200 nanoseconds. And then the horizontal amplifier it receives. So there will be a brief time span in which the horizontal signal is remain horizontal. So that's why the delay line is used. What is trigger circuit? So from vertical amplifier, it is given to a trigger circuit. This is triggered by the portion of the vertical amplifier output. Okay, see the diagram. A portion of the vertical amplifier is given to the trigger circuit. Okay. Now this circuit initiates the time-based generator. It is the link between the vertical and horizontal time-based. Trigger circuit is used to synchronize horizontal deflection with vertical deflection. Trigger circuits triggers the input, which is the vertical amplified inputs. It triggers to the time-based generator so that it can be transformed the vertical signal into the horizontal signal. Okay. Now what is a time-based generator? Before the horizontal, we'll see the time-based generator. Okay. What is a time-based generator? Here we convert a vertical amplified signal into a horizontal amplified signal. Sorry, horizontal signal. Uh, how we are achieving it? Okay, we can't give just the input to the horizontal plates, or there will be a bit complexity. that's why we're taking the vertically amplified signal to the and converting it into the horizontal signal and then amplifying it with the horizontal amplifier to the horizontal plates in the cathode ray tube. We just can't give it to the directly to the vertical horizontal amplifier with the horizontal plates. Okay, that's why we're using this. Even this bit complex circuit, still we are using it. Okay. Now, what is this time based generator? The CLU is used to display a waveform that varies as a function of time. The waveform is to be accurately reproduced. This beam should have constantly horizontal velocity. Horizontal velocity displays that the plates are remain charged and the electron beams are pulled constantly towards the plates. Okay. As the beam velocity is a function of the reflecting voltage, the reflecting voltage must be increased linearly with time. As a beam velocity is a function of reflecting voltage, the reflecting voltage must increase linearly with time, which is what I said a ramp signal. A voltage with such characteristic is called a ramp voltage. As I said, it is a ramp signal which is ramp voltage. If the voltage decreases rapidly, zero, with the waveform repeatedly produced, observe a pattern which is generally called sawtooth waveform. You know what is a saw, right? How it will be just like somewhat this sharp kind of thing. Sorry, it is somewhat this sharp kind of thing. Okay. So it is like a tooth and it is in the form of a saw. So voila, we name it as sort of waveform. So the time taken to return to its initial value is known as the Faraday or return time. Time-based generator. Wait, let us see the sort of first. So see here, this is the sweep time, flyback time. Sweep time, flyback time. See, it is in the way of a saw and the arrangement of a tool, which is continuous. And this horizontal amplifier, which is voltage and time. Okay. Now, how are we? This is like a basic input present at the horizontal. It gets mixed with the horizontal vertically amplified signal with this, and then we are going to get a horizontal amplified signal. So time-based generator is used to generate sawtooth voltage and required to reflect the beam in horizontal section. In sawtooth waveform, the deflecting voltage increases slowly and linearly with respect to time and reduces to zero quickly. The rise time and the fall time is less. Now, you generally understand what is time-based generator, right? Comparing combining the sawtooth waveform signal and the vertically amplified signal, we are able to generate a horizontal signal, right? Now the most CRTO vertical amplifier we have done, DN9 horizontal amplifier, time-based generator to signal. We have to see horizontal amplifier. Okay, horizontal amplifier is similar to vertical amplifier. What an vertical amplifier does, it takes an input, it vertically amplifies the signal, which is the required amount of signal for the electron beam to pull towards itself so that the output signal is similar to the input signal. Okay, the same is going to be done through the horizontal amplifier. It gives the required amount of voltage for the output signal, for the input signal, for it to expand the beam into a waveform of signal. Okay, let us check a bit of notes. Sorry. So there are nodes. This is the general nodes. This is it. So just have a just a fluorescent screen. What is a fluorescent? The fluorescent screen is a screen which is fixed at the end of the cathode ray tube, which is the output of us, like which is the only visible part of it. There will be various tune which has time with various frequencies of time. Frequencies means various time periods like nanoseconds, seconds, microseconds, nanoseconds, microseconds, milliseconds, okay. So we can adjust it. So based upon the adjustment of it, we can check the time period of it, okay. And then the signal, horizontal signal, and then there will be and then there'll be adjuster, okay, vertical adjuster and horizontal adjuster. What it does is, and the signal, the heat, due to the heat of the cathode ray in the electron gun, and the physical malfunctions which you do, there will be disformation inside the electron gun, which leads to the midpoint will be a bit far away from the line, will not be at the exact level. So we have horizontal and vertical adjusters. We give a check signal uh, which is present there. A pin will be given as check signal. Okay, the input from the CRT, we have 5 volt. We'll give it as a input to the cathode tube, as the input of the tube. Ground will be provided within itself. So it will be a sine waveform. We know that the supply to the home is 50 hertz to the voltage, three-phase signal, 400 voltage, three-phase signal. Okay, which is sine waveform. AC means sine waveform, which is alternating signal. The time the power is alternate, the voltage and the power is alternating with respect to time, which is VI cos phi. The power signal, the power of a signal is given as PVI cos phi. Okay, and this and apparent power and real power are different. Let's not get into that. So fluorescence scale is used. A fluorescence scale, and at the end is used. Now, what material it is made of? It is phosphor. So, so what material is made of? It is made of phosphor. Phosphor is used as K material on the inner surface of the CRT. See, it is like a funnel kind, okay? It is kind of a funnel. At the end, a grease piece, the inside coating of it is made of phosphor, okay? Phosphor. So, phosphors absorb the energy of the incident of the electron, okay? Electron is a charged particle, and we are given acceleration, pre-acceleration, post-acceleration, and a focus beam so that it has a good amount of velocity to it. So when it strikes on the phosphor is getting excited. When let's get better into chemistry a bit. Okay, what happens when excitation occurs? What happens when an excitation occurs? Now, when a low band signal, okay, or low band element or low band signal jumps to high band, okay, just we know that the valence bond and high bond, low bond, okay. So when excitation occurs, there is heat and light generated, okay. When excitation occurs, heat and light is generated, or we can also say vice versa. When or heat or light is given to a medium or element, the phase shift, the electrons will get excited, okay. The electrons will get excited. Now here, when the phosphor is tried with a beam of electrons, it excites, and light is excited. Light is given out, which is what we see as a bright dot, okay, which is a light green, neonish green. Okay. The spot of light is produced on the screen where the electron beam hits. So where the place is incident on the screen, that is the place where we can see, which indicates that the electron beam is pointing at that spot. Okay, when we don't give any input, electron beam is right to that spot. Now, the bombarding of electrons striking the screen release secondary emission of electrons. So phosphor has a valence bond. Okay, phosphor itself has a valence bond. When an electron strikes, the existing electrons go backwards, which creates a light, which gives secondary emission of electrons. This is the primary emission of electrons. From that, when it's striking with free velocity, that velocity gets deeper through, and secondary electrons are emitted. The valence shell is known as primary electron shell, and then the later will be secondary, ternary, and tertiary. Secondary shell, when secondary shell is being emitted, it gives light. which exits light, which is what a shining screen of light on the screen of the screen is produced. These electrons are collected or trapped by aqueous solution of graphite with aqua DAG, which is connected to the skin anode. Now, first I say the screen, and then a phosphor is screen material on the inner surface of the CRT. After that, we have a aqueous solution. Okay, these electrons are trapped by aqueous solution of graphite made of carbon. Okay, carbon. So trapped by aqueous solution of graphite known as aqua DAG. Aqua DAG is the name of the graphite with an aqueous solution. Okay, so when the secondary the electron is emitted from the phosphorus screen, it gets attached. Okay, it's attached to the aqua DAG, and that is what we can see as excited material. So collection of secondary material is necessary to keep the screen in a state of electrical equilibrium. So initially we get a brightness spot. Okay, as we change the waveform, it will changes. We need it to be at a frequent time so that we can check the values. Further, this aqua DAC, what it does is it constantly collects electrons so that we can represent the output for a small brief amount of time. I can't say it will be a 2 minute, 3 minute, 4 minute, no. 2 to 5 seconds, okay, 2 to 5 seconds it is. Now, the type of phosphor used determines the color of the light spot. The brightest available phosphide is P31 produces yellow green light with relative luminance of 99.99%. Just like sanitizers, which only kills 99.99% of germs, this is P31 has a yellow green light which produces luminance of 99.99%. Okay, 99%. Now, in the state of electrical equilibrium, which means the excited electrons or the secondary electrons emitted from the phosphorus screen is attached to the aqua DAG, which remains in electrical equilibrium, so that we get only a single signal for a single input. When it is not placed, what happens is if a signal is time, the amplitude is changing suddenly, we won't have a single waveform, we'll have a breakage of waveform. We know that the waveform should be continuous and differentiable at every point. Okay, continuous and differentiable at every point. So we don't need such disruptions in the signal. Okay, we don't need the signal, which is why we form a second layer called aqua DAC to have this kind of electrical equilibrium. Okay, you get that by fluorescent screen. So this together makes the cathode ray oscilloscope. So let me take a minute. Okay, let us quickly revise what is it. First, the input signal is given. Okay, first input signal through the probes which is present on a cathode ray oscilloscope. Okay, which is present on a cathode ray oscilloscope. Let me show you the diagram of a cathode ray oscilloscope. Wait a minute. It is not available now, so sorry for the interruption. Now, first input signal is given through input probes. Okay, the machine is somewhat. Let me draw small. It won't be exact. So it is what in shape of a tube. Okay, here we'll have the screen. This will be the screen. Okay, back side will be the input power supply. Back side will be the power supply. Let me write this. Okay, power supply. This is total power supply. Two backside cable, and we have three probes. Yeah, probe okay. One, two. One is for the input, another is for the ground, and one is for the check. And then we have here various type of knobs. Okay, knobs, little knobs, which we can adjust, as I said, the time, the frequency, the amplitude, adjustment horizontally, vertically, the bright luminescence of the signal, how bright it should be, and whether it is fixed equally or not to the line when it is given with the discharge. When the discharge is at the same position, correct position, that is when we can get the exact value of it. If it is a bit different or it changes, we cannot determine the phase angle, phase difference, the amplitude, or the time frequency of it. Okay, so vertical amplifier input probes are given the input to vertical amplifier. From vertical amplifier, it is given to delay line because we need both the vertical parallel plates of the CRT and the horizontal plates of the CRT to get the input at the same time. Okay, to get the input at the same time. So we use a delay line which is about 200 nanoseconds. It delays the vertical amplified input to the CRT by 200 nanoseconds, and a portion of it is given to the trigger circuit, which triggers the circuit to change vertically amplified signal to a horizontal signal, which needs to be amplified for the later. Next, it is given to time-based generator. What does a time-based generator do? It produces sawtooth waveform along combining with the input from the vertical amplifier through the trigger circuit. We are able to generate a horizontal signal. I won't say horizontal amplified signal, but a horizontal signal, which is then amplified and given as the charge to the plate. Okay, what do we do? Vertical amplifier delay line, from the delay line charge to the vertical plate so that the electron beam from the gun is vertically vertically amplified. Okay, vertically amplified, and a portion of it to the trigger circuit, to the time-based generator, to the horizontal amplifier, so that the in horizontal plates are charged and the electron beam is pulled so that the waveform is adjusted. And what is a CRT? What does a CRT have? An electron gun with a cathode, a heater, and the pins at the backside of the CRT. After the CRT, there are several focus plates or nodes placed. One is pre-acceleration plate, post-acceleration plate, and then a focus plate. The pre-acceleration post-acceleration has a high voltage, and the focus beam has a lower voltage comparatively. The signal pass through the electron gun passes through the focus beam as a single point, as a single ray of beam, and then vertical amplifier vertically amplifies the signal. Now it is in the form of a line, which then goes to the horizontal plates, which gives it as a signal, and it gets excited on a screen made with a phosphor followed by a aquadag. Aquadag is to create the electrical equilibrium between the phosphor and the aquadag. Okay, this is now. I think we left about the power supply. Let us quickly go through that. This is not a big issue. I think we first saw the power supply, but still, let us see. Uh, from this circuit itself, you should be able to know. We know that the amplifier takes only about 5 to 11. So maximum 11. We don't have that kind of circuit we can withstand greater than 11. It takes less voltage. Okay. So we need a low voltage supply to vertical amplifier, delay line, trigger circuit, average generator, horizontal amplifier, external input, and so on, so on, so on, so on. Okay. Keep it in mind. Okay. But the low signal isn't enough for the coil to get heated to excite the cathode electrons. Okay, it isn't surface. Okay, that's why we use a higher voltage, which means a higher voltage for the electron gun, and which is a part of the cathode ray tube, which means that a high voltage supply is given to the CRT and a low voltage to other parts of the CRT. Okay, this is what uh, a working of cathode ray oscilloscope or the components of it. Okay, at last the end of the session. Now types of the cathode ray oscilloscope. Uh, which we see is analog oscilloscope. Okay, because it is displayed in the wave form of a waveform. It just means that the signal's amplitude, frequency, time period, which is be calculated manually from the graph. We need to learn it from the graph so that we'll be able to do it. Okay, that's what it is. So categorization of CR is done on the basis of a signal, digital or analog. Digital can be classified as storage oscilloscopes. Now let us go to digital. I'll get into that what I want to say. A digital CRO. Digital, what does digital mean? It means ready to go information. What do you mean by ready to go information? For suppose, let us take a voltmeter, okay, and a multimeter, a digital multimeter, sorry, a digital multimeter and a voltmeter. In multimeter, we have various knobs for resistance, reactance, inductance, not inductance, I'm very sorry, ampere and current, okay, resistance, ampere, you just turn the knob to the respected value so that we'll get the exact amount of signal in numbers. Okay, in numbers. So based on the knob we turn, the output is given. So if we turn between 200 to the output 100 to 200, it gives value like 150. But in the case of a manual voltmeter, we connect it to the pins based on two coils, which is 10-volt coil or 5-volt coil. When it is placed in the 5-volt coil, the lower end of the value should be noted, which is on the scale. When it is given to 10, the upper scale is noted. So there is a bit of a discrepancy for that case. In CRO, as similar to CRO, when the waveform is produced, it is it does not be accurate. We are not able to calculate the accurate amplitude and period of it. Okay, that's why we use digital. In which the amplitude is calculated is given in digital waveform, which is numbers. So CRO, digital CRO offers digital readout of signal information, like how much amplitude, how much phase difference, how much time period, what is the frequency of the signal, so on and on and on. So it consists of an electronic counter along with the main body of CRO, which we learned of CRO is main body CRO, and from with that electronic counter is used to check the amplitude of it. Okay? Storage CRO. What is a storage CRO? As you can see, what is a storage CRO? A CRO which can store the information is known as storage CRO. Okay, it can be of it is can be no, it is a digital CRO which has the ability to store the data. Nowadays, I don't know the exact model, but we can see oscilloscope with a readout information. When we insert a pen drive, we are able to record the signal of it into it. Okay, so in this see storage CRO readings the display up so a substantial amount of time after first stage has appeared on the screen. The storage CROs are also useful for the display of waveform low frequency signal. So when the signal is of low frequency, we won't be able to check the exact, we won't be able to say the exact waveform of it. Okay, that's why a storage here we store and then amplify the signal so that we are able to see it. Or dual beam CRO. In you can see as you can see dual beam, which means just two electron guns, just two beams, two electrons. So we have two spots on CR cathode ray which are on the screen, which means we have double the power, two signals. So and dual beam of CRO, 12 beams fall on a single CRT. A dual gun CRT generates two different beams. These two beams produce two spots of light on the CRT screen, which make the stimulus observation of two different signal waveform possible. The comparison of input and its corresponding output become easier due to the dual beam CRO. At the starting, I said as an example of an amplifier, right? Here we can use it in dual beam CRO. But generally first CRO is for single input. Later on we have 2 to 3 inputs. In digital CRO we have 2 to 4 inputs. We can also connect multiple probes to it. Okay, so dual beam means to will give the input signal to it, which will be single sine form or the wave form, and then the output of it. The time period will be fixing so that the port waveform does not go out of range. It means it won't cut out of the screen which is provided. Okay, we adjust the time period, the voltage, and the amplifier of it, so that we are visibly able to compare the input and the output screen. So these are the types of CROs which we have used, and this is cathode ray oscilloscope. So at last, for screenshot, you can keep the screen, check it. Hope you have taken it. And these are the components of it. Okay. At last, takes here. I'm sure this video will be helpful for you in some way, education purpose, and thank you for waiting and seeing all the content of it.